Let's start. So this is the second lecture of the third week. So we have done the integration, definite integral and indefinite integral, and from today we are going to talk about improper integral. So I think this is somewhat unfamiliar to you because in high school curriculum I don't think they cover improper integral. So let me define rigorously what we are doing here. So let me read out the definition. So one can define integral of discontinuous functions. So I said that there are two types of discontinuity of functions. One is a function has a limit, but it's discontinuous because the value of the function is not defined. Another one is the function diverges at some point. So in this discontinuity, we are talking about diverging situation. Okay, and in that case, the definite integral on this continuous function is called improper integral. So for example, let's say f is a function which is continuous on the interval which is closed on the left side and open in the right hand side. And at the right hand side limit, the function diverges. The improper integral of f on this closed interval is defined to be the limit of integral from a to t, where t is the value less than b, and limit is taken when t goes to b. So, of course, this limit is the left limit. T approaches to b from the left-hand side. So if this limit exists, then we define improper integral of f on this continuous domain. So for example, let me give a picture of this situation. We have asymptotic vertical line at b and a, and function is well defined from a to b, not b included. So we have this type of function, y equals to f of x. So when we take an integration from a to t, where t is less than b, we are taking the area under this graph from a to t. Okay. Now what we are doing here is sending this t to close to b from the left hand side, so that this area approaches to the area under this graph of over this interval a to b. So if the value of this area converges to finite number, then we say this value is the improper integral of the function on this interval from a to b. Okay. So this looks like definite integral, but this is not definite integral because f of b is not defined. Okay. So this is not a definite integral. Because fb is not defined, and moreover, not just because fb is not defined, but also because f of x, the limit of f of x diverges when x goes to b. Okay. All right. So there's another situation of improper integral. You can set your domain from a to infinity and still define an improper integral if the limit of a to t integral exists when t goes to infinity. So in the previous example that I draw in the blackboard, you have a finite domain, but in this case, the second case, you have an infinite domain. So the f of x could be bounded function for entire a to infinity, but you may have an infinite area under the function, right? So the limit may or may not exist. So we are checking whether the limit exists, and if it exists, we can conclude that the improper integral exists. And there are other situations that the discontinuous point lies in between of interval of domain. So for example, let's say we have a function defined on entire real line except for the 0, okay? So at 0, if function diverges, you cannot assign any value so that the function becomes continuous. I'm sorry, so this is a typo. F is a continuous function on R except the point, sorry, except 0, except 0. Then we can define an integral as a sum of integrals, one from minus infinity to 0 and the other from 0 to infinity. And if the sum of these two improper integrals exist, or two improper integrals exist, then we say this improper integral from minus infinity to infinity exists. So in order to define this type of integral, you should have both improper integral exist. If one of the improper integral diverges, then you say this improper integral, the total improper integral, diverges and does not exist. So let me give an example here. First of all, let's look at 1 over x squared defined on 1 to infinity. So when we try to compute the improper integral, you have to take a limit of integral from 1 to b of 1 over x squared dx, right? So this is a definite integral because b is a finite value. So when you do the definite integral computation, you get this one, okay? So basically, we are taking a limit of 1 minus 1 over b by taking b to infinity. So when b goes to infinity, this part goes to 0, so it converges to 1. So since limit exists, improper integral exists, and its value is 1. So you can imagine that the area under the graph of 1 over x squared from 1 to infinity is 1, although this area is not bounded. This area approaches to 1 if you're looking at the long tail of 1 over x squared. And also, let's look at the improper integral of 1 over square root of x from 0 to 1, not 1 to infinity. Now, this type of function is not defined at 0. Simply, you cannot plug 0 in the denominator. So let's try to follow the definition. First, in order to compute this improper integral, you have to take the limit by sending the lower limit of integral from says a to 0 and take the limit of this integral. So when you do the definite integration, you get this formula, 2 minus 2 square root of a, and when a goes to 0, this part goes to 0, so you get 2. So that improper integral exists. Now, this also means that the area under the function of 1 over square root of x from 0 to 1 is approximately 2, because the area is not bounded. You have a you have a long neck inside of the region. So for example, if you draw the graph of functions, so this one for 1 over x squared, so 1 to infinity, you have area, which is unbounded. It goes to diverge almost approximately 1, is it right? We had 1 here. So this is the graph of y equals to 1 over x squared. And the other one for y equals to 1 over square root of x. Now we are taking a domain from 0 to 1, and this looks like this one. And the area under this curve from 0 to 1 is also unbounded here. So there's unbounded region here and in here. Still, we have the area approximately 2. Okay, so these are two examples, two standard examples of improper integrals. Okay, here's a tricky problem. So suppose that we have 1 over x minus 1 cube, and we are taking a definite integral, 0 to 3. Now, it seems like definite integral because the limit points 0 and 3, the function 1 over x minus 1 cube is continuous. It's well defined. So if you assume that this is definite integral and try to do the definite integration by using the standard formula of indefinite integral, you can try in this way. So first, take the indefinite integral of 1 over x minus 1 cube and get this antiderivative and try to plug in 0 and 3 so that you get 3 over 8. And that's wrong. Why is it wrong? Because in the domain of 0 to 3, you have this continuous point 1, x equals to 1 of this function. So when x is 1, the denominator becomes 0, so this function diverges. So this is not a definite integral. This is an improper integral of the type 3 that I put it in the definition. So how to do the improper integral? You have to split your integration from 0 to 1 and from 1 to 3. Okay? So in that case, you have to do the computation twice. So for example, you have 0 to 1, x minus 1 cube dx, and that is equals to 1 over 2 x minus 1 square 0, 1. Now, in principle, I have to take the limit of b and send b to the left-hand side of 1 and see where the limit goes. But I can just simply take this integration and I can just simply abbreviate all the limit notations and so on by just putting 1 here. So what happens is on the top limit here, I have to plug in 1 here in the denominator, and the denominator becomes 0. So I can imagine that if the upper limit goes to 1, that this whole thing goes to diverge. So this does not exist, diverge. And same thing for 1 to 3. So we have x minus 1 cube dx, and this is 1 over 2 or 1 and 1, 3. And also in this case, lower limit cannot be plugged into the antiderivative because it diverges. So it also diverges. So if you try to graph the function of 1 over x minus 1's cube, the function looks like this. So you have x-axis and y-axis and 0 and 3. And here you have 1. And when x is less than 1, I have to take this x-axis a little bit higher here. So when x is less than 1, the value is negative, and when it approaches to 1, it goes to negative infinity. So it's from minus 1 to 1. You have asymptotic line, vertical asymptotic line here, and then it diverges to negative infinity. And when x goes to 1 from the right hand side, you have positive infinity and decrease to 3. Okay. So this is the picture, and simply these two computations says that the area of this part and area of this part both diverges. So this diverges to infinity and this diverges to infinity. Now the question is, we had the computation previously, the wrong computation, but we got some finite value, 3 over 8. What does it mean? So simply, this is wrong in the sense of our definition of improper integral, but we got some number, and this should have some meaning or some interpretation. What does it mean? What does 3 over 8 means? So forget about the definition that we defined previously. There's another way of defining the integral of a function which is not continuous. So how do we? What's the another way? So you have a function discontinuous at the middle of this interval, right? So what we are going to do is take an equal distance, take an interval around 1, which is equally distributed from 1. So let's say we have 1 minus t to 1 plus t, okay, from here to here. So this is just a side note, another way of defining. So this is simply another definition of improper integral. Improper integral. So for example, if you want to compute 0, 3, 1 over x minus 1 cube dx, then this is nothing but limit of when t goes to 0. First, you take the integral from 0 to 1 minus t. So I'm not going to write the integrand because there are going to be lots of integration here. And then next, you take the integral from minus t to 1 minus t to 1 plus t. 1 minus t to 1 plus t. Okay? And then next you take the integral from so this is not necessary here. just take a integral from 1 minus t to 1 plus t. Okay, and then 1 plus t to 3. Okay. So when t goes to 0, we are taking this sum of areas from 0 to 1 minus t and t plus 1, 1 plus t to 3 approaches to the original red area. Okay, so the difference between the previous definition and this definition is that in the previous example, previous definition, we are sending the upper limit of the first integral to 1 independently to the lower limit approaches to 1. So there are two limits of the first integration and the second integration. And for this this definition, we have one limit. So the integration is done by one limit by sending t to 0. By doing this, we have a canceling between this area and this area as t approaches to 1. Okay, so when you compute this part this way, you get 3 over 8. So this is just simply a different point of view of looking at the area of unbounded region. So you can define your area to be sum of the sub-areas, or you can define your area, unbounded area, to be a limit of something that's considered as an entire subset. So let's say this yellow part, the union of all yellow part is one big subset of the unbounded region, the union of red parts, and then you're going to take the sequence of these sub areas by enlarging it a little bit and little bit larger by taking this t goes to 0. So that's where the 3 over 8 comes in. 미안합니다. Sorry. I forgot to convert the screen here. Okay. All right. If you have any question, please ask right here. I will give a few seconds. No. So the question is, what's the difference between? So let me rephrase the question. So you're asking whether this 1 over x minus 1 cube it seems different from the previous one. So I think there's an error in your question. So in the definition, we have, I think you're talking about the third statement here. So let me make it bigger here. So in the third type of definition of improper integral, zero is not a continuous point. However, the f of x does not have a limit. Okay, so we are assuming, because this is an improper integral, that we are assuming that the function f of x diverges at 0. Okay. So by finishing up the first question, so 1 over x minus 1 cube also is a similar form of type 3 improper integral. Although the total integration is from 0 to 3 instead of minus infinity to infinity. However, the 1 is the point where the function diverges. So 1 over x minus 1 cube falls into the third category here. Okay. Okay, so second question, you don't have to take the integration of the middle, because this part, so basically we are taking a yellow part of the region and trying to enlarge it so that it covers the entire red area. So when t goes to 0, this yellow part will eventually cover the entire red area. So we don't have to take the integration from -1 minus t to 1 plus t. And also we don't have any method of integration of -1 minus t to 1 plus t integration, because that would be using another definition of improper integral, and we don't want the definition of improper integrals to mix. So this is a totally different way of defining improper integral. Okay, so does it answer your questions? Okay, so let me move on. So this is a theorem that also we're not going to prove this. Let's say we have two functions defined on the same domain, and there is a strict inequality between value of functions. So f of x is always bigger than or equal to z of x, and we also assume that these functions are positive functions. There is an easy way to do this using the theorem that we mentioned. Simply take another function that you can take an integrations and see the inequality between two functions. So when you have x, let's look at the x bigger than 1, okay? Then we have e to the negative x squared always less than e to the negative x, right? So, or equal. Now, if you try to take the integration from 0 to infinity of e to the negative x squared dx, although 1 is not a discontinuous point, you can simply, as a like a definite integral, you can simply take the sum of integrals from 0 to 1 of e to the negative x squared and 1 to infinity of e to the negative x squared for convenience, okay? So this is a definite integral. Definite integral. So this converge. What about the second part. This is the improper integral. Improper integral. And the convergence and divergence of original improper integral depend on the convergence and divergence of this part of integral. Okay? So we only need to check whether this integral converges or not. However, since we have this inequality, we have e to the negative x squared dx is always less than e to the negative x integration. And what's the integration here? So you can simply take the antiderivative of e to the negative x as minus e to the x and taking 1 and infinity as a limit point. When you plug in infinity here, you get 0. And when you plug in 1 here, you get e to the negative 1. So you get e to the negative 1. So this converges. So this converges, which implies that this part also converges by theorem. Okay? So what's the conclusion? This part converges, therefore this integral converges. So when you're looking at the convergence and divergence of improper integral, you only need to take the tail of the integral. So if the first few interval is if the first integrating the first few domain is hard, then you just take that part away and then looking at the tail of this domain of integration. And what about the other one? So we have log x, and we are going to take an integration from 0 to 1. So there are two ways of looking at this integration. One is simply looking at the meaning of improper integral. So you have a log function, okay? So from 0 to 1. So let's say 1 here. So log function looks like this, and we are looking at the area, unbounded area under the curve, okay? So we are checking whether this area diverges or converges. However, log is an inverse function of exponential function. So if I invert this graph, this is a graph of y equals to log x. But if you invert this, it looks like this one. So y equals to e to the x. And we are looking at this part, right? Or if you take the mirror image, then you can take e to the minus x, and this yellow area is the area under the log function, right? So you can imagine that this should be equal to the integration from 0 to infinity of e to the negative x dx. And that's simply 1 by simple calculation. So you can imagine that this is converging. This improper integral converges. Another way of checking whether this converges or not is you can take a usual antiderivative, like indefinite integral of log function. Let's say we have y, let's substitute log x as y, then dy is dx over x. So we get x from 0 to 1 of y x dy. So when x is 0, y is negative infinity. And when x is 1, we get y equals to 0. And x equals to e to the y, so y e to the y dy. So and then let's switch this one. So we have 0 to negative infinity y e to the y dy, and since we switch the limits, we get negative sign here. And also, let's replace y to negative y. Okay, so then you get 0 to y of minus y e to the negative y minus dy. Okay, so you get minus of 0 to infinity of y e to the negative y dy. Okay. Now this is also improper integral. It's not it's continuous at 0 because if y goes to 0, this goes to 1 and this is 1. So only this continuous at this infinity. So let's compute this by integration by parts. So first you take the integration on e to the negative y, you get y e to the negative y because there's a negative here, and 0 infinity minus of the derivative y here, so we get 0 infinity of e to the negative y dy. So looking at this one, we have first you have to plug in infinity to y. So when I plug in infinity to y here, this is polynomial, and this becomes 1 over the exponential of infinity. So when y approaches to infinity, polynomial is always increasing smaller, the rate of increase is smaller than the rate of increase of exponential function. So this one goes to 0 when y approaches to infinity. You can check by L'Hopital's rule and others. And also when y is 0, then this also goes to 0. So everything goes to 0 here. So 0. And what about this one? This is simple. This is minus 1. Okay. This entire thing is 1, so it's negative 1. So there are two ways of checking whether this is convergent or not. Okay, so let me move on. If you have any question, please stop me anytime. Let me give another example of improper integral. So you can check whether this weird function is convergent or not using standard technique of integration, and also the second one. I think the second one is easy, simpler. So let me give two examples here. Okay, so second one, we have 0 to 1, 0 to 1 of log 1 plus x dx. Now, there is you have to ask whether this is actually an improper integral. Is this improper integral? It looks like improper integral because this function is not defined at 0, which is the left limit of this integral. However, if you take the function log 1 plus x over x, this function has a limit at 0. So the limit of this function, so it's a right limit of this function is, now the numerator and denominator both goes to 0, so you can use the L'Hopital's rule. So that the denominator is 1 and numerator is 1 over 1 plus x. So this is 1. So if you draw the graph of this function, this is actually not defined at 0, but has the limit value 1. And I think it somehow decreases. So it's somehow like decreasing. And when it becomes 1, it becomes log 2, right? So this is actually looks like a continuous function. If you assign a value of function at x equals to 0 as 1. So it's nothing but a definite integral because it means the area of this bounded region, okay? So this is not a, you can say this is not an improper integral because it's only discontinuous at one point and you have a finite value as a limit. So this is not an improper integral. But finding the actual integration value is different question. So I'm not going to do this here. You're only checking whether this integration converges or diverges. So the conclusion is, therefore, it converges. How about the second one? So we have 0 to infinity of sine x squared dx. Okay. Now, you cannot take the integration like this. So you have to substitute x squared as y so that we get 0 to infinity of sine y, and dx becomes dy equals to 2x dx, so 2x dy. So if you rewrite this, then it's 2 square root of y sine y dy. Okay. Now, still, it's not easy to take derivative integration. So let's use integration by parts. First of all, let's take integration on the sine part. So we get minus cosine y to y and 0 infinity, and minus minus, you have 0 infinity of cosine y, and take the derivative of 1 over square root of y, we get 2 times of y, 3 over 2 times 1 over 2 dy. Okay. Now, so let's look at this part. Okay, so let's look at I'm sorry. So this part. Okay. So before we do this, forget about 0 here. Forget about 0. Now, as I mentioned before in the previous example, when you have a finite value on some interval, you don't have to look at the value of the integration on the subintervals. So sine x squared has finite value from 0 to say 1. Okay, so to check whether this improper integral converges or diverges, you don't need to take the integration from 0 to infinity, but you can only take the integration from some finite value, say 1 to infinity. Okay, so let me just take the integration from 1 to infinity. Okay. Now, then we have this part. First, when I take the infinity to y, then it becomes 0, and when I put y equals to 1, then it's a finite value. So this is finite. Okay. Now we only need to check whether this integral is finite or not. However, let's take this constant part away. So this part is nothing but minus 1 over 4 y cosine y dy 1 to infinity. Now the cosine y oscillates, right? It oscillates from minus 1 to 1. And if you're adding all these oscillating areas, plus areas and negative areas, it will become smaller and smaller somehow. We could make it bigger, but at least if the absolute value of all the areas are sum of the absolute values of areas converges. Suppose that we have this as a function of graph of y, so f of x, f of y equals to cosine y divided by y 3 over 2. This is 1 to infinity. Okay, so if you're adding all these areas as a positive areas, and if these sum of positive areas converges, then the sum of areas, positive and negative areas, also converges. So sum of absolute value of area converges, then sum of area, so with some sign, plus or negative, also converges. Okay? So we're going to take the absolute value on the integrand. So what happens when I take the integrand? So when I take the absolute value cosine y divided by y 3 over 2 dy, then let me give an inequality here. So cosine y absolute value divided by y 3 over 2 is less than 1 over y 3 over 2, right? So both are positive functions. So we have the integration less than y 3 over 2 dy. And what's the integral here? So we have y, here we have 1 over 2, so it's minus 2 e to the minus 1 over 2 from 1 to infinity, right? So when y is infinity, this becomes 0, so nothing happens. So when y is 1, we have 2. So this is 2. So we have convergent sum of total areas in between this axis and the graph. So therefore, the sum of areas with sign is also converges. So therefore, that means this integral converges. So this converges. So this we have a finite value here. We have a convergence improper integral, and therefore this integral it converges. So the original integration is 0 to infinity of sine x squared dx, and that can be split into two integrations, one from 0 to 1 and the other from 1 to infinity, and both are finite value. So we have a convergent improper integral. So if you have any question, please ask. I take that as a sarcasm. So If you have any questions later, then send me an email. Okay, so let's look at the gamma function. So we're going to talk about gamma function later. I think almost end of the semester. This is just the introduction, so you don't have to worry about understanding everything. So look at the definition of gamma functions. We have a function defined as a value of integral, but this integral is not definite integral. It's an improper integral. So you have to be careful that the gamma is a function of p, not in terms of x. Okay, so p appears as a power in the integrand of this integral. Okay, so in the picture, this is the picture on the right. It's the picture of the gamma function, the graph of gamma function. So it looks like so it has a negative value too. Let me draw in here. So when p, so this is the p. When p goes to 0, it diverges, and p goes to infinity, it goes to 0. And there's an asymptotic line at the negative integers, and the gamma function has this value. So let's say this is y, and this is the graph of y equals to gamma p. So for the negative value, so the positive value nothing makes problems. So in the negative value, how we define a gamma function is through this formula. So when x is positive, you always have this formula. Okay. So we define so gamma so x when x is negative as by this recursive formula by gamma x equals to 1 over x gamma x plus 1. So simply rewrite this equation in terms of gamma x. Okay. So it means that if you want to compute minus 1 over 2 gamma, then you can simply plug in here minus 1 over 2 and gamma minus 1 over 2 plus 1. So it's the negative 2 times gamma 1 over 2. So gamma 1 over 2 is well defined. Simply defined as 0 to infinity x to the negative 1 over 2 e to the negative x dx. Okay. So this formula is not hard to derive. You can derive this formula using substitution, not substitution, integration by parts. We can derive this formula. Let's do this. So first of all, what's gamma x plus 1? So instead of p, I used x, just for convenience. So this becomes t to the x, first plus 1 minus 1, right? So e to the negative t to dt. So that's the gamma x plus 1. And let's rewrite this, e to the x, t to the x. And using substitution, this is e to the tx e minus t 0 infinity and plus, and then take the derivative of t part. Okay, we get x t x minus 1 e to the negative t dt. Okay. So what happens on this part? So when I plug in t as 0, this becomes 0 because x is positive here. So we're assuming that x is positive. Okay. So when t goes to infinity, this is polynomial on the numerator, and on the denominator we have exponential part. So we get 0 because exponential always diverge faster than the polynomial. So this whole thing goes to 0. And this part, now x is constant, okay? T is the integration, integrating variable. So we have x times the integral of t to the x minus 1 e to the negative t. And that's the definition of gamma function. So that's gamma x, okay? So what we have here is gamma x plus 1 is equal to x times gamma x. So that's why we have this formula. So we're going to define the negative value of gamma using this recursive formula. And for also, the positive part is purely by this improper integral. Okay. So from this part, it's simple application that I think many of you already know about these ones. So first of all, let me briefly read out the definition here. So you have parametric curve parameterized by two functions, ft and gt for x and y coordinates. And if t ranges from a to b, so when time moves from a second to b second, then the length of this curve is given by square root of the sum of squares of derivative of two functions. So basically you can assume that this is the velocity. Okay, so velocity. And this f prime t gives the x velocity, and this is f prime t, right? F prime t, and y prime g prime t is the y velocity. So if you use the if you just add these two velocity, this is the velocity at the time t, and you're taking a speed of this function because you're going to add the length, right? So speed is the length of this velocity by taking the square sums and taking square root. So that's why we get the length, right? So when you have a cycloid, cycloid is the trajectory of a point on a unit circle rolling over a surface, flat surface. So you have an equation of cycloid, parametric equation as xt equals to t minus sine t and yt equals to 1 minus cosine t. So in order to get the length of one cycle, you have to take the integration from 0 to 2 pi of square root of x prime t, so this is 1 minus cosine t squared, and y prime t, which is sine square t. Okay. So if you compute your integration, and you get 8. Okay. Now this is another theorem to compute the area of a surface. So you have a 3D object. We are going to take the surface area. So first of all, let's take the graph of function, say this way, okay, a to b, and we are going to take rotation of this graph on x-axis. So basically you get this 3D object, okay? And then we want to compute the surface area, not the volume of this object. So surface area is given by this formula. So I'm going to explain why we get this one. And also, if you take your curve as a parametric curve, not the graph of a function, you can replace that with this formula. Okay. Let me draw a picture, a bigger picture to explain this one. So here we have a graph y equals to f of x, and we are taking a rotation here. Okay. So when we compute the surface area, we're going to slice the volume as a thin slices. So we have, let's take this slice, okay? And then we are going to take the surface area of this slice. So we are only taking this thin strip which covers this slice. So this slice is at x position, and the radius of the slice is the length, the value of function. So f of x is the radius. And how about the width of this slice? So width is not the dx. So width of this volume is dx, but width of this strip is not the increment of x. So when I enlarge this part, what I have here is this curve, let's say x to x plus delta x. So I can almost approximate this length by tangent line, which is y equals to f of f. I'm sorry. Okay. So let me write this xi here. Okay, xi. So y prime xi x. Let me write in above. So this linear approximation is y equals to f prime xi x minus xi plus f xi. Okay. So using this approximation, so I started from f of xi, and I ended at this point x. When xi is delta x, I get f prime xi delta x plus f xi. Okay. So the length between xi to xi plus delta x is approximately the length of function is length of tangent line from xi to xi plus delta x, and that is square root of the increment of x, delta x squared, and increment of y, which is f prime xi delta x squared. So this can be written as square root of 1 plus f prime xi delta x. Take the delta x squared outside of the square root. So this is the small length of each line, and we're going to add the surface area of these small strips. So the surface area, the total surface area, is sum of small strips which is 2 pi fxi times the width of this each strip, which is 1 plus f prime xi square delta x, and sum of this area of small strip is the when I take the smaller and smaller strip and when I increase the number of strips. 들리시죠? 들리세요? 네, 조금 크게 할게요. 저거 배터리가 다 돼가지고. Okay, so that's the first part, and the second part, it's almost similar. We have 또 꺼질 수 있어가지고 미리 좀 연결을 해놓고 할게요. 이건 괜찮겠다. 자, so for the second part, we have a similar situation, but now we have xti, yti to xti plus delta t to yti plus delta t. Okay, so we are going to take the length of the curve of small interval as approximated by the length of the line connecting these 2 points. So the length of the line connecting these 2 points is given by the xt plus delta t minus xt I square plus yti plus delta t minus yti square and square root, and this is the length of segment from ti to ti plus delta t. Okay. So then let's take the delta t divided on each side and then multiply the delta t outside. So we get this formula. So delta t xti plus delta t minus xti square, and then yti plus delta t minus yti delta t square, and in the outside of the square root we have delta t. Okay. So when delta t goes to 0, because we are going to split this entire curve into infinitely many sub-segments, what happens to this fraction is that this becomes x prime ti, okay, square, and this becomes y prime ti square. So approximately, okay, delta t. Now, we're going to add this length by taking the radius at each ti as yti. Okay, so we're going to add the area of this surface, small segment. Okay, so total area is sum of all 2 pi y ti of this width x prime ti square y prime ti square delta t. Okay, so when I increase the number of segments, I get 0, a to b. So a and b are not the bound of y, it's the bound of t. So when t equals to a, we are at here, and when t equals to b, we are at here. So 2 pi y t square root x prime t square y prime t square dt. So that's the surface area. Okay, so this is a example. You can just simply use this formula, the previous formula, to compute the surface area of a donut, so I will skip this one. And also, if you want to compute the volume, depending on which axis you're rotating on, you can use the different formula. Let me write this one. So let me give a picture. So remember these formulas. So we have, if you have a volume obtained by rotating around the x-axis, you're also going to take the slices here. So, so slices now has radius equals to, so if the slice is at x, then the radius is f of x, and the width is equal to delta x, and the volume of each slice is 2 pi r square, which is pi f square, and the width is delta x, and you're going to take all the sums of this volume. So when I take infinitely many slices, then this becomes the total volume, and the summation becomes the integration of pi f square dx. Okay. So this is when you rotate around x-axis, and when you rotate around y-axis, then suppose that you have function y equals to f of x like this one, and by rotating around y-axis you get this figure. In this case, you're going to take a slice perpendicular to y-axis. So this is the slice. So this slice has radius x, right? So when slice is at y, you have an x, so this point is x comma f of y, f of x, which is y. The radius is x, okay? And how about width? Width is increment of y, so this is delta y. So basically you get sum of pi x squared delta y. as a total approximate volume of this rotation. But when you take the infinite slices, you get, now let's say y is from c to d, okay? Then I get c to d of pi x squared dy, okay? Now this integration doesn't seem right, because the x, of course you can take it as a inverse function of y, but it doesn't seem right to just looking at this formula how to take a how to take an integration. So I'm going to take it as an integration in terms of x by plugging in y is equals to f of x. Okay. So when y is c, assume that my x is a. Okay. So this is our original graph of function. So assume that when y is c, x is a, and y is d, then x is b. So now dy equals to f prime x dx. So when I substitute dy, I get f prime x dx, and now integration is on x, and pi x squared is not changed. Okay. So this is how you get. I'm sorry. So there's also typo. Okay, so this is another there's a typo here, right? So in the, if the graph is rotated about y-axis, then not this one, this is pi x squared f prime x dx. Okay, where did this come from? 2 pi x 2 pi x f of x. I don't know where it come from. Okay, so this is the right formula, right? Okay, so this is the end of the slide. I think we are over time a little bit. Let me give brief computation on the first example. So we have y equals to square root of x, and x bounded by xy and y0, and rotate about x equals to -1. Okay. So let me graph this function. This is y with the square root of x, and bounded from x equals to 4, and in that case y equals to 2, and y equals to 0. So bounded by 3 curves, these curves. Okay. And we rotate that around the x equals to -1 axis. So here. So this is a rotation. So when you rotate this, you get a figure. Looks like this, right? So on the middle it's empty, and on the side we have a filled region. So how do you take the volume? So we're taking volume, right? So we're going to take a slice perpendicular to y-axis, right? So we get each slice looks like annulus. This annulus, and this slice has width equals to delta y. Okay, and how about the area? So the area is area in between two circles, right? So we have area equals to pi larger radius, which is 4 square, minus pi smaller radius, which is x, right? So we get x squared. So sum of areas, sum of volumes of each slice is the total volume. So we get total volume given by pi of 16 minus x squared delta y. And by taking an infinite sum, you get now y is from 0 to 2. 0 to 2 of pi 16 minus x squared dy. But now let me change back this y in terms of x, because y is square root of x. So when y is 0, x is 0, and y is 2, x is 4. So pi 16 minus x squared, and dy is square root of 2, 1 over 2 square root of x, and dx. It seems a weird dy equals to what's wrong in here? So I think something went wrong. Sorry. So I have to take a rotation about x equals to -1. Okay. So I'm sorry. So this is 5. So this is 5, and this is x plus 1, right? So let me change all this. So we have 25 minus x plus 1 squared delta y, right? And then this becomes integration from 0 to 2 of pi 25 x plus 1 squared dy, right? Yeah, sorry. So, well, if you change your y in terms of x, then I think we get the same problem, that we have a square root of x in the denominator and we cannot take an integration. So instead of taking y into x, let's take x into y. I think it's simpler. So in that case, we get 0 to 2 pi 25 minus, so x is y squared, so this is y squared plus 1 squared dy, and this is an integration of polynomial, so I think it's not hard, so I'll leave it as an exercise. And the second one is the homework, but let me give a hint of how to do this. So first of all, we are taking a circle of radius 1 and centered at 4, 0. So this is the center. This is the curve. And we are taking a rotation about y-axis. So we get a donut by rotating this figure. We are going to take a volume of this donut. So consider this is the field surface, field region, and then rotate around y-axis. So you're going to take a slice perpendicular to y, okay? So when you take a perpendicular slice to y, then you get a similar figure as this one, so analogous, like a pineapple ring. So this is the symmetric about the x-axis, so you can only take the upper part volume and then twice it in order to get the total volume. Okay, so the definition for the center of mass is the following. You can simply memorize, or you can use Archimedes rule to derive this formula. But so this one is the center of mass for the one-dimensional object. Okay, I'm sorry. So let me switch back to. Okay, so for the center of mass, this definition gives the center of mass of one-dimensional object. If you have a two-dimensional or three-dimensional object, then you can extend the definition by changing this variable x to y and change the function delta as the function of density at that position, either x, y, or z. So the density at that position means that the total mass per area or volume attached at that point. Okay. I think in physics that will be covered, I guess. But if it's not, then I will explain it later. Okay, so this is it for lecture, and if you have any questions, please ask right now before we move on to the MATLAB. Okay. So MATLAB. 저장해놓은 게 없네. Okay. So last time we talked about symbolic function, right? And also integration. Let me try to graph some functions that we mentioned in the lecture. So, for example, let's try to look at what this function look like. Log x plus 1 divided by x. Okay. So I define this function as an anonymous function. So and then when you draw the function, you have to set your array of domain. So you have to set you have to first define the array of values lies on the interval of domain of the function. So for example, I want to graph this function from 0 to 1. So this becomes t times ft. Lens space. Okay. So you see, doesn't matter what happens at the 1. It happens at t almost goes to 1. It goes to finite values, so it doesn't diverge. Okay. And let's also graph some surface. Okay, so when you rotate the graph of a function, you get 3D object, right? So I want to draw the surface of the 3D object. Okay, So when you make a 3D object, a surface plot, you have to take two variables to graph it in two-dimensional surface in 3D space. So let's say I want to draw the graph of donut. Okay, surface of donut. So when you graph the surface of donut, you need two parameterization. So first one is the parameterization of t, where x plus let's say 4 plus cosine t, and y equals to sine t. Okay. So let me write it that way. So we have x as a function of t, and x as a function of t, y also as a function of t. Okay. And then what you need is another function which measures the degree of rotation of this point on the circle. Okay, so this t measures the position of a point inside of circle, and I need another variable to determine the point of the rotation and determine the angle of rotation. So let's say this is let me call that a p. Okay, so I need t as a angle between 0 to 2 pi, and p as a degree angle between the same 0 to 2 pi. Okay, so but the role of these two variables is different. One is for rotating the point inside of circle, and the other is rotating the point along the y-axis. Okay, and then I have to make a mesh grid. So I have to take, let me just give an example how we do this before I explaining all the details. So mesh grid of TP. Okay, so by doing this I get 2D array from one-dimensional array of T and P. So and then let's define another variable z, because now we have a 3D object whose each point has 3 coordinates. So let's see. So what we have here is the center is at 4,0. So let me change this to z here, and then now y, so this is TP, DPP, and TP is now 4 plus cosine t times cosine p, and here we have sine p. So I hope this go well. Okay, so we have surf x tp, y tp, and z tp. Grid. Sorry, so grid. Okay, it looks like donut, believe me. So let's say x is equal. Okay, it looks more donut. So when you try to graph a 3D object, you can only draw the surface of 3D object. How you do that is try to set two parameters which determines the point on the surface. And in this example, we had T for measuring the meridian and the other for longitude. So let me draw a picture here. So, 가깝네. Okay. So here we have section. This is a figure of section of the donut here. We're going to rotate this circle. So I switched the y-axis and z-axis so that it looks nice in the figure. So this is t. So t measures cosines. Yeah. The t measures the angle between the x-axis and the point, and t measures the angle between x-axis and this arrow inside of circle. Okay. So when I try to map, and then f measures the angle between x-axis and the circle on the other side. So we have this is p. Okay. So in general, when you rotate your circle, so your circle moves by p angle. Okay. P angle here. So if you try to determine the point on this donut, you also have to be provided with this angle t. So what's the coordinate in this case? So first of all, if you project your point onto the xy plane, the distance of the projection to the origin is this length, which is 4 constant, plus the cosine of t, right? So this is the length between zero and this projection. Now that's not enough to determine the position here. So this only simply means the length, the radius between the origin and the projection. Now, in order to determine the x and y coordinate, you have to take the radius 4 plus cosine t and multiply with the cosine p, the angle of rotation of this circle. So that's the position of x, x coordinate of the point. Okay, so this is x, and y is obtained by taking a product of sine p. Okay. How about z? So z is just simply height. So when we have an angle t, you have a height of sine t. So that's how you get the three coordinates in terms of t and p. So if you make each value of t and p, you determine the unique point in the donut. So when you try to graph the surface, you need to have array of t and array of p, two one-dimensional arrays, and you have to make it as a two-dimensional array because this surface is two-dimensional. So the mesh grid here makes your one-dimensional array two-dimensional array by mixing this t and p, and then by plug in t and p, a two-dimensional array variable, inside of this function x, y, and z, you get array of x coordinates in two-dimensional array, in array of y coordinates, array of z coordinates, and surf command somehow meshes the points together so that looks like a surface, a smooth surface here. So if you enlarge this figure, it's actually a patches of flat rectangles. So it's like when you graph a function in MATLAB, it's just the union of straight line segments. So same thing for when you're graphing the surface, it's a union of flat surfaces, but in a bigger picture, it looks like curved surface. Okay, so I think it's almost over. So let me give a demonstration how to submit your homework, how to submit your quiz. 자, 이거는 그냥 한글로 할게요. 예를 들어서 좀 확대를 해야겠다. 자, 예를 들어 가지고 잘 보일지 모르겠는데 보이나? 어플 보시면은 어플 창을 한번 가서 보시면은 아도브 스캔이라는 게 있어요. 그러니까 지금 여기 잘 안 보이시죠? 여기 구글 검색할 때 좀 단서가 돼서 아도브 여기까지 쳐도 벌써 나오는데 아도브 스캔이라는 게 있거든요. 스캔 하시면은 이거 까시면은 여기 하고 이제 이게 사진기로 내가 문서를 PDF로 만들 수 있어요. 찍어가지고. 그러니까 예를 들어가지고 여기다 한번 써봅시다. 이렇게 써서 썼다고 해봐요. 잘 안 보일 수도 있는데 잘 보일란가 모르겠네. 자, 일단 보시면은 이게 직각으로 놓고 하면 제일 잘 되는데 잠깐만요. 여기서 이렇게 하겠다. 직각으로 놓고 하면 제일 잘 되고 그러니까 이렇게 약간 사선으로 돼 있어도 잘 인식을 해요. 그럼 저희가 이제 이렇게 찍어가지고 이제 문서로 인식을 하고 여기서 이제 계속 누르면은 여기 이제 저장이 돼 있죠. 이렇게 PDF로 만들어지거든요. 여기에 이제 PDF로 저장. 이제 폰에 저장이 되겠죠. 그럼 요거를 올리시면 돼요. 뭐 요거를 이제 뭐 컴퓨터로 옮겨가지고 올리시든지 아니면 뭐 폰에서 바로 올리시든지. 요거 하는 데는 별로 시간 안 걸리겠죠. 그러니까 한 5분 정도, 5분에서 10분 정도 드릴게요. 퀴즈 푸는데 한 30분, 그리고 나머지 이렇게 PDF로 변환해서 올리는데 한 5분에서 10분 들여서 그 시간 내에 제출하시면 돼요. 네, 공책에 해도 이게 경우가 좀 명확해야 이게 잘 되는데 그 있을 거예요. 저기 뭐야, 애플에도, 애플 스토어에도 아도브 그게 있을 거예요. 그리고 뭐 아니면 스카이 스캐너인가? 뭐 그런 것도 있고 많이 있어요. 그래서 뭐 어떤 걸 쓰든지 PDF로 변환해서 올리시면 돼요. 그러니까 PDF로 변환하라는 이유가 아니면 제가 그러니까 뭐 어떤 사람은 뭐 그림 파일로 하고 이렇게 하면은 LMS에서 열 때 되게 불편하거든요. 그래서 아무거나 중에 하나 쓰시면 돼요. Okay, so that's it for today, and thank you for listening. See you next week. If you have any questions, please leave a comment. Thank you.